So I started listening on my videos and I realized I said okay in the beginning of them. So I guess I am trying to avoid that from now on. So we're now in chapter 11, and chapter 11 deals with VSEPR, valence shell electron pair repulsion. Well, it just starts here, I guess. It goes over this different types of bonding. And VSEPR is one of them. Well, it's one of the theories. It's actually, this theory is wrong. So we're covering some wrong theories right now. So, and VSEPR is a wrong theory, but why are we covering it? Because it works most of the time, and it makes so much sense. And people were actually kind of upset when they found out this theory was wrong, and then the much more bulky, cumbersome quantum mechanics is the right theory with the molecular orbital theory. But well, let's go on. Let me teach you misinformation. Well, not really. It's not misinformation. It works most of the time. So, okay. Now, the VSEPR, the way it works, so valence shell electron pair repulsion. Valence is outside shell, so the outside shell, electrons repel each other. And if you see in this picture here, we have beryllium dichloride. And these chlorine atoms, think of them like really big balls of negative charge. And so these big balls of negative charge want to be as far away from each other as possible. And how does that work? Well, the farthest away they can get from each other is to be in a line. So let's pretend on the right I have this dance floor, and you have someone in the middle, and there's two people. And the idea is that the two people are attracted to the person in the middle, but they are completely repulsed by each other. So how do they dance with this one person at the same time? Well, they form a line. That is the best. And what happens when a third person enters? The third person's coming to the dance floor. What happens? Uh, Forms a triangle. So actually, let me go. Here's another one. Carbon dioxide has it. And when we're going through these things, it doesn't matter if it's single bonded or double bonded or triple bonded. It's just something that's there. It's an electron group. So a double bond does not count as two, it counts as one. So third person comes in and it forms, and then what we form is trigonal planar. So definition, 3 points define a plane. So we have a plane here. And so 360 degrees is a circle. So if you have two things, 360 divided by 2 is 180. 360 divided by 3 is 120 degrees. Or if you prefer radians, it'll be 2 pi divided by 3 radians. I prefer degrees myself. Okay, so now let's move on and talk about a molecule like formaldehyde. Formaldehyde is here on the right. And you have the carbon double bonded oxygen and 2 hydrogens. So remember, I told you 3 things. Doesn't matter if it's single bonded or double bonded. Those are 3 groups, all bonding. But oxygen, as I've drawn here, has these lone pairs sticking off of it and these big areas of negative electron density. So what happens is it repels the hydrogens, and the hydrogens creep forward. They creep forward a little bit. So rather than being 120 degrees, the bond angle between the oxygen and the hydrogens is about 122 degrees. So it creeps it forward a little bit. So what about 4 things? So in the dance club, of course, we dance on a plane. That would be, we would form a box around the person. What would happen though? Atoms and molecules can go 3D, and because of that, they form tetrahedra. So three groups, four bonding groups forms a tetrahedron. And the perfect angles in a tetrahedron is 109.5 degrees. So what happens, that's if you have all the same bonding group. What happens if you have a lone pair? Well, it squeezes the bonds a little bit more, and it turns out, so with ammonia here, with that extra lone pair, it brings it down to 107 degrees. And now you can see here's a difference between the electronic geometry and the molecular geometry. The tetrahedral geometry, this is the 4 things all bonding. This is the electronic structure, But where the molecules are, where the atoms are, this forms what's called a trigonal planar. So three things, I'm sorry, trigonal pyramid, I'm sorry, trigonal pyramidal structure. And if you have a tetrahedral with two bonding groups and two lone pairs, this forms a bent structure. And see, water here has an even shorter squeeze in there. So ammonia it's squeezed to about 107. Water squeezed it a little past 105. So that was electron pair valence shell electron pair repulsion. The repulsion. They are repelled. They are very repelled, and showing here. And here, tetrahedral structure, that's methane, CH4. They're all tetrahedral electronic structures with the lone pairs, but the tetrahedral molecular geometry, the ammonia has pyramidal, so trigonal pyramidal structure, and water has bent. It's a V shape. Okay, moving on, what about five things? So five things is known as bipyramidal, trigonal bipyramidal geometry. And it's kind of like a trigonal planar, and what's along there is called the equatorial plane. The three chlorines are along the equator, and then above and below is known as axial. So it's perpendicular to the plane, right? So, and this, if you have a plane and you have perpendicular, that's geometry is if it's perpendicular, a line is perpendicular to the plane, it's perpendicular at every single point. So, and the equatorial plane, the lone pairs go in there first. So here is phosphorus pentachloride. We covered this last lecture, and has the planar along the equator and then axial above and below. And when lone pairs are added to this, though, they add to the equator. So if you have one lone pair with the bipyramidal electronic geometry, this is known as a seesaw. So that molecule here, as drawn, is a seesaw, and it's kind of like a seesaw if you used to play that when you were a kid. Here is another one. If you have two lone pairs, they go along the equator, and this molecule is called T-shaped. So it's like a funny looking long T with a really long tabletop kind of T. And then another lone pair there for three. So bipyramidal electronic geometry with three lone pairs, like xenon difluoride, which we covered last class. This is a linear geometry. Okay, so what about six things? Six things is known as octahedral geometry, and every bond angle is perpendicular. So everything is perpendicular, and this is an octahedron. And if you look at fluorite, so if you octahedral geometry is the same thing as cubic geometry. If you look at fluorite, you can see octahedral fluorite. You can also see pyrite also has a similar cubic geometry, so you can get pyrite octahedra as well. I said it's the same as cubic. If you have a cube and you put a dot on each of the six corners or six faces of a cube, and you connect them, you'll get a octahedron. So octahedron and cubic geometry are actually the same thing. And let's say you're missing one. We have one lone pair with that. This is known as a square pyramid, kind of like the Egyptian pyramids is a square pyramid. This is different than the trigonal pyramidal structure that ammonia has. And then if you have two lone pairs, this is known as square planar. So here, xenon tetrafluoride has that. There's a cancer drug called cisplatin. That's a square planar. It's a very common cancer drug that has that geometry as well. Okay, let's summarize. And so here is the summary. And if you have two electron groups and they're both bonding, then this is a linear electronic geometry. I'm going to include hybridization now. We're going to talk about bond hybridization later. But anything that has linear electronic geometry is going to have an sp hybridization. So carbon dioxide is an example of that. So if you have three electron groups, the hybridization is going to be sp2. And if they're all bonding, then this is going to be a trigonal planar molecule. If you have if you have 3 electron groups, 2 bonding, and one of them is a lone pair, this is a bent structure. So SO2, sulfur dioxide, is an example of that. Ozone's another example. So let's move on to 4. If you have 4 items, this would be an sp3 hybridization. So 4 things being a bonding atom or a lone pair. So if you have 4 things and they're all bonding, you're going to have a tetrahedron, and that's a tetrahedral molecular geometry as well. If there are 4 things, 3 bonding, 1 lone pair, this is tetrahedral, still electronic geometry, sp3 hybridization, but the molecular geometry is trigonal pyramidal. Trigonal, however you want to pronounce it, pyramidal, and I usually just say pyramidal. This then, like ammonia. Ammonia is an example. And then go one more, 2 bonding, 2 lone pair. This is bent. Water is an example. I'm including another one. If you have 4 things, 1 bonding, you have 3 lone pairs. It's still tetrahedral geometry, but it's a linear geometry. And hydrofluoric acid is an example that I just put that there. But it's just 2 things. If you have 2 atoms, it has to be a line between them. That's the only way to draw it, really. Okay, let's move on to bipyramidal, so trigonal bipyramidal structure. And for every single molecule that has this 5 bonding, 5 electron groups, is going to be sp3d hybridization. So of course we'll cover hybridization later, but I'm including it now. 5 things, all bonding. Then we have bipyramidal geometry. If you have 1 lone pair, the lone pairs go along the equatorial atoms first. Then that becomes a seesaw geometry. If you have 2 lone pairs, it becomes T-shaped. 3 lone pairs, linear. So, okay, and moving on to octahedral geometry. If there are 6 electron groups, you have sp3d2 hybridization. If they're all bonding, that's octahedral geometry, electronic and molecular geometry. For 5 bonding, 1 lone pair, this is going to be a square pyramid. And 4 bonding, 2 lone pairs, this is going to be a square planar. And later on, these shapes are going to become important because we're talking about bond polarity and if a molecule is polar or not. So you will reference this. This is another thing you do not have to memorize. This will be provided for you if needed. So join us next time for more explorations in chemistry.